Hi, this is Mr. Mac. This is another concept video. Today, I actually want to talk a little bit about our concepts of solving systems of simultaneous equations. Now, first of all, let's take a look at an equation in two variables for just a second. Any equation in two variables is going to be generating a list of ordered pairs that make the equation true. Let's just take a look at a simple linear equation like y equals 1/2 x plus 3. When x is 0, y is 3. When x is 2, y is 4. When x is 16, y is 11. When x is -8, y is -1. Now, all of these ordered pairs, and there's an infinite number more of them, actually are such that if you put the first number in the ordered pair in for x and the second number in the ordered pair in for y, they will make that equation true. So this equation right here, this linear equation, or this equation in two variables, actually generates an infinite number of ordered pairs. It's impossible to look at this and say, oh, well, x has to be 14, because it doesn't. There is a y that's matched with x's. Now, if we had another linear equation, let's just maybe use y equals 3x minus 2. How's that? Now, this equation in two variables will generate ordered pairs like 0, -2, -5, -13, 7, 19, and so on like that. Then there's an infinite number of ordered pairs that make that particular equation true also. Now, mathematically, if we link these two equations together and consider them a system, then the question becomes, what ordered pair or ordered pairs makes both of these equations true at the same time? Okay, that's why they're sometimes referred to as simultaneous systems. What ordered pair or ordered pairs make both or make all of the equations in our system true at the same time? Now, what we're going to do right now is we're going to focus mainly on linear systems. Now, with linear systems, the equations actually generate straight lines. And what we're going to see is that if we have a linear system, let's just see if we can graph these two equations. So just draw a quick graph. Y is equal to 1/2 x plus 3. We would have 3, and we'd have this one. And this would be just a quick sketch of perhaps what the graph would look like for the blue equation. And then 3x minus 2, here's -2, and if we go 3, so we're getting something that looks like this for the green equation. Now, notice every point on the blue line is matched with an ordered pair that makes the blue equation true. Every point on the green line is matched with an ordered pair that makes the green equation true. Now the question becomes, what ordered pair makes both of these equations true at the same time? Well, now, if we have a picture like this, the graph of the system, it turns out that the place where the two lines intersect is a point that is on both lines, and so therefore that point is matched with an ordered pair, or should be matched with an ordered pair, that makes both of the equations true at the same time. Now it looks like it's about the point 2, 4. So let's try that. See if we put 2 in this, oh, well, here it is right here in this first list already. And if we put 2 in here, we get y equals 3 times 2 minus 2, that's 6 minus 2, or 4. So 2, 4 is also a point in that set of ordered pairs that makes the green equation true. So we would report the solution to this system as the point 2, 4. Now, if this system is linear, then if the two lines are different and they just intersect in one point, there will only be one solution. There are a couple of other things that could occur. We could have two equations that name actually the same line. They look different, but they name the same line. If that occurs, then what we have is an entire line of ordered pairs, of points that are matched with ordered pairs that make the equation true. If the if the two lines are actually parallel, then that would be a system that has no solutions. So with linear systems, you could have a system that gives you just one point of solution, or a system that gives you infinitely many points of solution, or a system that gives you no points of solution. Let's just go ahead and kind of make a little chart on that. Now, see, if we're talking linear systems here, the possibilities are one, two different lines intersecting in one point. Now, when that occurs, we say that the system is consistent. Generally, consistent means there is a solution, and independent. That means that the lines are not the same, they are different. Now, if we have two equations that actually name the same line, then we will have infinitely many solutions Now, be careful here. If we say we have infinitely many solutions, we do. That doesn't mean that every pair of numbers will be a solution. Let's just as simple here. If I have 2x plus 3y equals, let's go with 6, then, for example, the ordered pair 0, 2 is a solution. And let's give ourselves a second line here. Let's do 4x plus 6y equals 12. Now, if you look at this closely, you can see what I just did was I multiplied through the first equation by 2. So 0, 2 is still a solution here. Also, the point, let's try 3, 0 is a solution to both of them also. Now, notice the point 5, 1 is not a solution because 2 times 5 is 10, 3 times 1 is 3, and 10 plus 1 is 13, not 6. So even though we have infinitely many solutions, there are a lot of ordered pairs that aren't solutions as well. So when you say infinitely many solutions, that does not necessarily mean that every point in the xy plane is going to be solution. That just means all the points on that line will be solutions. Now, the third thing that could happen, by the way, when we have two equations that name the same line, we say that the system is consistent and dependent. Now, consistent means that there is at least one solution. Dependent means that the two equations are not different. Now, the third thing that could happen is we could have two equations that name parallel lines. Now, when you have two equations that name parallel lines, there is no solution because the lines don't ever meet. That's the definition of parallel lines. And when that happens, we just say the system is inconsistent. That's another way of saying that there isn't a solution. So there are three types of occurrences. We have systems that give us one-point solution. The lines intersect in one point. The system is consistent and independent. We have systems where the two equations really are the same equation. They just look differently to start off. And there they name the same line. We have infinitely many solutions. We say the system is consistent and dependent. And then if we have two equations that name parallel lines, they don't intersect, there's no solution, we say the system is inconsistent. Now, one more thing that needs to be discussed here is a business application that you all should be aware of, and that's the idea that if you have a business, sometimes there are two different things that you look at. You look at the income, in other words, money coming into the business, and you also look at the expenses or the costs, the money going out. And a lot of times, these will be functions. There'll be a function that tells the income in terms of something that the company is doing, and then there'll be expenses in terms of something the company is doing. Imagine, for example, your company makes little brown boxes of some type for some reason, and people seem to want them. And it costs a certain amount to make the boxes, and then you to ship the boxes and sell the boxes, and then money comes in and so forth. And so you have a function that tells you the income your company is making based upon how many boxes they make. And then you have a function that tells you the expenses the company incurs based upon how many boxes they make. Now, where these two intersect, where the income and expenses intersect, we call that the break-even point. And companies aspire to get past the break-even point so that the income will be more than the expenses, or at least that's the hope. I mean, if you work harder and harder and do more and more, and the expenses become more than the income, then you're really not doing something right. So a lot of times when you're doing these kind of problems, you're going to be graphing two functions, an income function and a cost or expense function, and then you're going to take a look at where the two meet, and that will be the break-even point. And I think that pretty well takes care of this particular concept. So we're done.